Let's start analyzing graphs of functions, and we're going to focus on some key terms and important concepts. We've already talked a little bit about domain and range. So if I give you the graph of a function, you should be able to find the domain and the range of that function. So let's start with the domain. I could use my handy dandy domain detector and slide that across my graph, and I'm taking x values from negative infinity all the way to x equals positive infinity. And when this domain detector hits the graph, it beeps. And so when would it beep as I slide this across the screen? Well, it would start beeping here. What's the x value at that point? Draw an arrow here. X is equal to -4. So it starts beeping at -4, and then it keeps beeping. Notice here, even though there's an open circle there, there's still a point right above there. So at x equals 1, it's still beeping. And then it continues beeping, and here it's going to stop beeping just for a second. What's the x value there? +4. And then it's going to keep beeping after that. And this arrow at the end says keep going, all the way to infinity. So from negative infinity, it doesn't start beeping until I hit -4. And then all the way until x equals 4, it stops for a second. And then it keeps beeping for the rest of the time until I get to infinity. So for my domain, use a D for domain. It started at -4 and it went to +4. So it beeped at -4, but it did not beep at 4. So we're not including +4. And then union with, and then it beeped from 4 to infinity, but once again, not including the 4. And infinity, we always use a parenthesis because it's not a number, so we're not going to include that. All right, what about the range? I want to find the range for this function. Well, then I would have to use my range detector, which I have right here. And this time it's going to go from y equals -infinity until y equals infinity. And so when would it beep as I slide this across the screen? It won't beep there. What's my y value? That's a y value of -2. But then it starts beeping. Keeps beeping. Here it's hitting the graph in 2 spots, but it keeps beeping, and then there, even though we have an open circle, we still are hitting the graph here, and we're hitting at all these points on this horizontal segment here. And then it keeps beeping, and then finally that's the last time it beeps, and then it stops beeping after that y value, which is 6. So when did it beep? From -2, but not including -2, all the way up until we hit 6, including the 6. So our range, we use capital R, from -2 to +6, we're not including the -2, we had an open circle there, but we are going to include the 6, so we put a bracket. So it's pretty easy to see when you have a graph. What happens if you had just an equation? Find the domain and range of this equation. All right, so there's a couple ways to deal with this. And I like to just think about what's going on here. And I'll show you a few other ways in a minute. All right, so I want the domain. So in other words, what values can I plug in for x? When I look at this expression, I see I have a square root. I know that I can take the square root of 0. Square root of 0 is 0. I know I can take the square root of positive numbers. Square root of 2 is 1 point something, right? But I know I cannot take the square root of negative numbers, at least not yet, not in the real number system. Once we open it up into the complex number system and talk about imaginary numbers, we'll be able to do that. But for now, we can't take the square roots of negatives. So for my domain, as long as my square root winds up being 0 or positive, and what would make this expression here 0 or positive? Well, if x was 3, I'd get 0. Anything bigger than 3, I'm going to get a positive value. So my domain is going to go from 3 to infinity, and I could have it equal 3, so I'm going to put a bracket around the 3. How about the range? Well, once I plug in numbers that are 3 or bigger, what am I going to get here? I'm going to get at least a 0, and then plus 2 is 2. Or I'll get something bigger than 0 plus 2, and that'll be bigger than 2. So I know this, the least value I'll get for my function is when I plug in 3 for x, and I'll get g of x equals 2, or g of 3 equals 2. So 2 is the smallest I can get, and then it can just keep getting bigger and bigger and bigger as x gets bigger and bigger and bigger. So there's my range. So I like thinking about it that way. Now, what some people would like to do is they look at this and say, oh, square root, whatever's in the square root has to be greater than or equal to 0. I'll add 3 to both sides. That doesn't change my inequality. So I get x greater than or equal to 3. Oh, so 3 to infinity. Got it. Well, that seems so much easier. I didn't have to think. Math is about thinking. Okay, you want to have conceptual understanding. You don't just want to try and memorize steps to do. So that's why I usually don't teach it that way. Another thing we could do, though, is we could think about the graph. And you think about, what's the parent function look like? What's the square root of x look like? Well, the square root of x, we should know, looks like that, right? And then what if I subtract 3 inside the square root? What does that do to my graph? Well, that's going to shift it 3 units to the right. Okay, how about the plus 2 after the square root? What does that do? Well, that's going to give me a vertical shift of up 2. And now, with my graph, what's my domain? Oh, x equals 3 to infinity. What's my range? Y equal 2 to infinity. So that's another way. And it's important to always try and make these connections between equations and graphs. All right, what else should we look at? We need to talk, we've talked about it already a little bit. The vertical line test helps us determine whether a graph is a function. So y is a function of x if and only if no vertical line will intersect the graph at more than one point. So if you can draw any vertical line that hits your graph in more than one point, then the graph is not a function. So let's take a look at this. Here we have a graph. And I want to know, is y a function of x? So what I could do is I could draw myself a vertical line. Let's set that up. There we go. And notice, if I drew my line right here, it's going to hit the graph in 2 points. And actually, there's a lot of places where I could draw a vertical line, and it's going to hit the graph in more than 1 point. So this definitely is not a function. Y is not a function of x. But then there's an interesting question here. Is x a function of y? And so that means, let me take my vertical line over here. Let's rotate it. Could I draw a horizontal line that hits my graph in more than one spot? And the answer to that is no, I cannot draw a horizontal line that hits it in more than one spot. So that means that x is a function of y. Another way you could think of it is if I take my graph and I rotate it like this. And now my vertical is the x and the horizontal is the y. And now I could apply the vertical line test to this one. And is there any vertical line that hits the graph in more than one spot? And the answer to that is no. So it turns out that yes, x is a function of y, but y is not a function of x. Another important concept is we need to be able to find the zeros of a function. And you have heard of all of these terms already, but you may not realize that they all mean the same thing. So the zeros of a function mean the roots of the function or the x-intercepts of the function. These 3 terms are synonymous. So any question that asks for one of these, we're referring to the same thing. Okay? If we're thinking about a graph, where does the graph cross the x-axis? Those are the roots, those are the zeros. So let's look at an example. What if I ask you to find the zeros for this function? Now we're not looking at a graph, and so we're going to have to try and figure this out analytically. Now let's back up for a second. Let's say I have some function, and let's say it hits the x-axis here and maybe over here. And the function could look like anything. I don't know, let's say maybe it comes like this, like that, whatever. I have some random function. This isn't the function f of x for this example. I'm just drawing a function. All right, what do you notice about this? The roots, the zeros, the x-intercepts, those are the x values where the graph hits the x-axis. Okay, so whatever these x values are. But what do you notice about any point on the x-axis? What's the y-coordinate for this point? Well, it's 0. What's the y-coordinate for this point? Well, it's 0. Every point on the x-axis has a y-coordinate of 0. So once you realize that, finding the zeros of a function is basically setting y equal to 0, or my function f of x equal to 0. So I get x cubed plus 3x squared minus 4x equals 0. So what do I do to solve this? Well, maybe I can factor it. If we can factor it, then we can use the zero product property. I notice that each of these terms has at least an x to the first power. So let's factor an x out of everything. That would leave me with an x squared plus 3x minus 4. If you distribute the x back through, I always do that just in my mind to make sure that I factored it correctly. So if I went ahead and did that, x times x squared is x cubed, x times 3x is 3x squared, x times negative 4 is negative 4x. So I always double check as I'm factoring. All right, so now I have a trinomial. We've spent a lot of time in algebra factoring trinomials. And so when I do that, I know that these first two terms multiply to x squared. So that's going to be an x times an x. And I know after doing a lot of distributing or foiling that these two multiply to negative 4 and they should add to 3. And so what's that going to be? Well, a plus 4 and a minus 1. And so if you distributed or foiled, x times x is x squared, x times negative 1 is negative 1x, and then we're going to get a positive 4x, and those are like terms, which gives me a 3x, and then 4 times negative 1 is negative 4. So I know that I've factored this correctly. Okay, so now we can use the zero product property, and we can set each of these factors equal to 0. So either x equals 0, that's one solution, or x plus 4 is equal to 0, which means x equals negative 4. That's another solution. Or x minus 1 is equal to 0, and therefore x is equal to 1. We have a third solution. And a little later in the course, we're going to learn that with polynomials, the degree of the polynomial is the highest power of x. So this has degree 3. That a polynomial of degree 3 has at most 3 real roots. And we actually had 3 in this case. Now what we could have done is we could have graphed this and try and find the zeros that way. So let's take a look at that. If I use a graphing calculator and I put my function in here, so I have x cubed plus 3x squared minus 4x, and I just do it in the standard window, I can see that I have 1, 2, 3 places where it crosses the x-axis or hits the x-axis. Now I could guess and just try and trace along here to find where those are, but it might not give me the exact answer. But if I press second trace, it has an option to find a 0. And then it wants a left bound. So I'll go to the left. That's good. Enter. Give me a right bound, so I go a little bit past the 0. Enter, guess, enter. And there's my answer, x equals negative 4. And I could similarly get the other two answers. I'll show you that those work. I'll just hit trace and type in 0. And notice that's when x equals 0. And then if I type in 1, that gives me the other x-intercept. So we can use a graph, but sometimes you're not able to use a graph. And you should be able to do it analytically as well.